Just yesterday, I think I coded one Minesweeper AI on coding game, and I thought, yeah, that was using rule-based AI, and I thought it would be quite cool if we could do it using neural networks instead. So I did actually try to find like a Minesweeper environment, like using OpenAI Gym. Um, yeah, but let me just show you. Yeah, but however, I went to search through the documentation, and they actually don't really have a Minesweeper environment inside here. Yeah. Actually, do they have? Because if they have, we could just use it straight. Oh, they actually have Unity ML agents. Wow. Okay, maybe I should check it out because I do know how to use Unity. And yeah, do they have Minesweeper? Because if they do have a Minesweeper, then I could just use it. But it looks like OpenAI Gym probably doesn't have Minesweeper. So, you know what? Let's just write something here. Okay, Minesweeper AI. Okay, first step is to code out the game environment. Okay, so let's just we define a game environment called Minesweeper. We define Minesweeper. Okay, or rather we can call it a class Minesweeper. Okay, and then we can define the init function. Okay, and then maybe take in like board size. Yeah. Oh, okay, let's firstly just do some imports. So maybe like import numpy as MP, import math. Yeah, maybe these two. Yeah. So self.port equals to, so this just defines the port equals to mp dot zeros. Okay, so we do have yeah, maybe something like that. Yeah, then maybe we have something called step, which steps through with action value with a move. Okay, self dot port. Okay, move. So the move will be a tuple. Yeah, self dot mod move. Okay, so okay, what we need to do, maybe we need to also define like render. Okay, so what we do is for rows in self.port, okay, print rows. Will that work? Yeah, I'm not too sure, but we can try it. So self.port move equals to 1. Okay, let's just try something simple first. We do a very, very simple environment like that. Okay, let's just try. Okay, okay, maybe like 999. Okay, 99 first. Okay, okay, so that's okay. So environment dot step, maybe like the move here would be like maybe 3 5. Yeah, so over here did have the thing coming out, so that's great. Okay, so I don't quite like the representation right now. We got to change the representation a bit. Okay, so perhaps if the square has not been opened yet, I can call it maybe I don't know, if we're gonna go by numbers, maybe we call it number 9. Oh, okay, actually 0 is fine. Maybe what we'll do is instead of having mp dot zeros, we could do like we could basically do a number array, or should we do a character array instead? So we could do something like this: self.bot equals to, okay, so size by default maybe we can set it to be 99, and then like the mines will be maybe 9 mines. Yeah, self.bot equals to question. So what we'll do is, okay, so okay, so we can do something like that: height with mines, and then what we'll have is we can have self.bot equals to Quite like this kind of representation actually. Like this is actually quite nice already. Just maybe what we can do is we can find a way to do the zeros different. Like if we have a now there, we could perhaps. I'm just thinking how can I do it, because if I do like empty dot zeros, mm, okay, I got it. So I mean we can just do like that. We can just do a question mark. Okay, so what we can do is like maybe like self dot minds equals to, we want to like do a random sample from this. So numpy dot random dot choice generates a random sample from a given 1p array. Okay, so we sample 9 times from this, replace equals to false. Let's do something like that. We basically do this from a range here, and then we replace equals to false. This will give us like a list of numbers that actually contain the mines. Okay, and this will be the board. So let's see whether this. Okay, so I don't quite like the way this is rendered. Okay, initially it was fine when it was numbers. If I do like question mark, it kind of spoils the grid. So perhaps what I can do is I do space instead. Okay, so like that. Okay, so that wasn't great. Yeah, maybe this would do. Yeah, this will tell us that all these are blanks. Yeah, but this doesn't give us the edge cases. So okay, 1, 2, 3, 4, 5, 6, 7, 8, 9. Very good. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, in fact we can even do like height plus 2 also. Okay, just that when we print here, we can do like for rows in self dot board. Yeah, we can do something like this so that we don't print out the top and the bottom row, because these are like fillers. Okay, so it's all going to be blanks now. And then we have a self dot mines is this. We can also print out the mines actually. Render with mines. We can copy the array. Okay, and then what we'll do is basically for for mine and self dot mines, what we'll do is we'll just display the mines. So self dot board, okay, mine divided by heights. Okay, we actually kind of need this, okay, like that. Okay, mine divided by self dot heights. Okay, Okay, this we should convert into an numpy array so that we can use this later on. So mine divided by self dot height, mine percent self dot height equals to maybe a star, and then we can then print this out like that. Okay, render with mines. Okay, it did not quite work out. Uh, let's just see what's environment dot mines. Okay, yeah, we do have the mines already in the environment. Okay, but somehow we are not able to. Okay, somehow we are not able to get the mines to be displayed in this environment. So let's see why this is the case. Okay, so it's supposed to be like this: self.board. Oh, because I put in self.board and render. Okay, let's try again. Render with mines. Okay, so these are the mines. 2, 3, 4, 5. Okay, so I realized this part here actually um, because this was a filler to just display the ages here, it should not be displayed. Okay, what we should do is we should actually just push the mines like +1 here. Okay, because we kind of gave a buffer for the grid. Okay, oh, why is there a 1? Okay, because I did a step. Okay, so with the mines we can see that it's like that. So maybe we also define a reset thing. So we can call our reset function like that. Okay, self dot reset. This one will be self dot width, self dot height. Okay, self dot height, self dot width. Okay, let's try again. Self dot reset. Okay, oops. Environment dot reset. And what we can do is we can then render with mines. Yeah. Okay, so this is a new set of mines that will be shown. Okay, so that's great. Now what we want to do is we want to create this step function here, which basically says that when we open up the board, okay, we want it to like maybe have a dots or something like that to basically show that it's a empty board. Like here we should like put with dots when there's no mines in that vicinity. So maybe we do a helper function first, like find mines, and then this will be a position here. So this will just returns the number of mines in returns the number of mines in the vicinity of the current position. So we already know what is our mines position here. Okay, so it is quite easy to basically find out how many mines there are. So what we can do is like this. The position will be given as the x and y, so like the row and the column. So what we can do is we can basically find out using the this position value. Okay, so okay, we have the list of mines. Okay, what we can do is we can get basically the positions of the okay based on this position. Okay, so maybe you can call it like that. Row column equals to position. Okay, and then what we can do is for x offset or row offset in okay if basically the if row plus row offset okay, times self dot width plus column offset. Or actually, what we can do is we can just like count the number of elements between like this one and the mines set. It's okay, we can just do this. It's a very fast operation. If row plus row of, but maybe we should optimize this because if we do neural network training later, we want it to run as fast as possible. So let's see whether I can optimize this. If row plus row, I think it's fine. Yeah, in self.mines. Then we will basically like put a num mines. Yeah, let's just do this. Num mines is like that. So basically, self.bot move equals to find mines move. Yeah, so the move is basically a position that we key in based on the row and column. Find mines is not defined. Okay, self.find mines. So we do have like a 0 here, okay, which is wrong, right? Because like this is supposed to give you one mine with this around. So what we need to do is we need to figure out why this was given a 0. Okay, why was this given a 0? Mm, why was this given a 0? Let's see. If row plus row offset plus some self width plus column offset in self.mines. Okay, so it depends on what is this row and column position. So it's 3. So and it depends on this mine position as well. Um, let's just print this to make sure it's working correctly. Okay, it printed 24, which means uh, this is row 2, which is 18, row 2, column 8, 1, 0, here, 0, 1, 2, 3, 4, 5, 6, 7, 8. No, row 2, column 6, 0, 1, 2, 3, 4, 5, 6, which is correct here. So it means that this 3, 5 is given wrongly. So 3, 5 should be 0, 1, 2, 3, should be here. Okay, so this one is actually a 2 comma 6, which is actually valid, is within here, which means that my mines itself is printed wrongly. So like this 24 should be printed as self dot, it should be self dot width actually. Self dot minebot, this one plus 1. So like 24, it should be printed at 3 comma. Okay, we look at this. Self dot width is basically the 9. So 24 divided by 9 is 2. So it should be here. And then the remainder for this, if we do that, is remainder 6. So 0, 1, 2, 3, 4, 5, 6. That's correct. But if we do like this, 3, 5 should be 0, 1, 2, 3, 3, 0, 1, 2, 3, 4, 5. Should be here. So the number is printed wrongly actually. This number here is printed wrongly. Yeah, I think I printed the number wrongly, which means that my step here, this part is wrong. So this part should be okay. Now it's correct. Now it's correct. Okay, now we got the okay. I think we have gotten the right number already. If we do the render now, we can see that it's 2. Okay, but now the next thing is that we need to expand out our grid so that we like enumerate over all the possibilities. Like once we get 2 over here, we want to like basically spread out all our. We want to open up the cells basically. So you want to open up all the adjacent cells if they are not already open. Okay, so maybe what we'll do is we'll have a like placeholder thing for the ages, like maybe because I don't want to open the ages. I mean, it makes no sense to open this side here. Either that or we can don't display it. So we can do it like that. Render rows. Yeah, we can do this. Mm, yeah, I don't want to open up the sites actually. So okay, so what we do is like this. We will check the neighbors of our board position and then we open up those that have not already been opened. So we can do the same call here. Okay, so for example, if we want to have this, we want to open up the cells that are not already open, we do this for row offset or column offset. Then we just check whether or not has it been opened. Okay, if grid, this one plus 1, and then this column plus column offset plus 1, okay, not equals to space. Okay, and basically we want to also check whether it's within the bounds. So I guess the easiest way will be to just like give another symbol for board edges. But if not, we can also check the boundary conditions here. And yeah, we can also check this part here. So what we can do is like that. If row, if this is in 0 or self dot height plus 1, means like 0 or 10. Okay, will we ever get to 10? Actually, it's 9, right? 0 or 9. Okay, because it's v plus 2, so yeah, we will get to 10. Yeah, 0 to 10 or column plus column offset in 0 or self dot width plus 1. Okay, continue. Okay, we do not want to process out of bounds. Okay, if the particular grid cell is a blank, okay, then what we'll do is we'll just basically call a step on that self.step. Okay, so this is actually called a flood fill algorithm to actually like iteratively open up the board. So we can do a self.step, and we can open up that move. So what we can do is we can then do this. Yeah, like that. Grid is not defined. Okay, so this should be self.grid, self.board actually. Oh, okay. This should be equals to blank, not equals to blank. So only when it's blank then we open up. Okay, let's try again. Just now it repeated too much. Okay, so we need to stop somewhere. If let's say the number is a one, then we don't need to open up further because like you see right now it just open up the entire board already. Open up the entire board, but it's actually printing it wrongly. Is it printing it wrongly? One, two. It's not opening up the top. It's not opening up this. Right now it should open up everything. So this means that there's some issue with the flood field. Okay, it's not opening up this row here. So I need to investigate what's the issue. Yeah, this actually should be -1 because I have an offset over here. Yeah, we just do a -1 here. I mean, it's very confusing. I would like to avoid this as far as possible. So what we can do is we can do this. Yeah, we can just do a +1 here. Okay, this should be good. Yeah, good. Now we render the entire environment. So now the only thing left is that we don't want it to basically show those steps that have a number. So if the number is 0, we open up some more. Okay, if not, we stop. So if the cell is a 0. Okay, so like that. Yeah. Okay, so we don't have the thing right now. Okay, which is weird. Okay, so we have a 2 over here. That's good. we've gotten it already. It's just that the render with mines is it's not exactly copying the entire board. Maybe we do a copy dot deep copy, which copies the elements inside as well. So we import copy as well. Okay, so great. Now it expands everything. So if we see like the normal render, you will see that this is what we'll get, which is quite representative of what you see. You click one time, you open up the entire view for the mine, and that's actually quite good for the game itself. Okay. Okay. Now what we need to do is we need to have like an environment parameter where we have like self dot done equals to false, which means that the environment is not done. Okay, and also we want to have a self dot reward is 0. So if let's say the basically the okay, so we want to just check whether game has been won. So self dot check win. Okay, so we have the function called check win, which basically checks whether you have won. So okay, basically we want to check the sum of this space over here. So what we can do is we can do this. So just check the number of like uh, empty spaces left. Okay, so if self dot board 1 minus 1 1 minus 1, because we don't count the ages. Okay, if self dot board count, this one is 0. Okay, it means we have is basically the number of mines, which is self dot mines. Then self dot reward equals to 1, self dot done equals to true. So we have 1. Okay, otherwise, okay, else if okay, actually that's it. So if we have lost, we can also put here. So if okay, we can just check. Okay, if row times self dot width plus column equals is in self dot mines, which means we have written none. Okay, like return -1 maybe. If we hit a mine, return -1. Yeah. So over here, if num mines is -1, it means we have hit the mine. We can just like declare game over. Like and self dot done will be false. Will be true. Okay. Otherwise, we can then continue to call this. Okay. Let's see what happens now. NP, the array has no element counts. Okay, that's fine. We can actually do it like this. You can sum this. Very good. All right. So that's more or less like how it should look like. So we have an environment slowly being opened up one by one uh, by our agent. Okay, so okay, maybe I'll do another function called moves. Okay, maybe first we have, so the moves are basically positions that are equal to zero. So basically so we can have like a moves equals to like this. For I, for row in range self dot height, for column in range self dot width. Okay, we then just check, okay, whether or not there's a if board self dot board, okay, row plus one, column plus one. Okay, if it's equals to a blank, that means it's a valid move. Okay, in fact, we can actually have a counter for moves that will just like slowly get removed. Yeah, actually that might be better. So what we can do is like this. Maybe I will just like, then over here the step will be just like row times, yeah, this might be better so that we can have the move as in a move as index and mix that move. Okay, so this will be better. So like when we step here, we can just step like a number here, like 34. So we can have like self dot moves to be the entire I, for I in range self dot height times self dot width. So this will give us the total moves, and then when we actually take a step here, okay, we will just basically remove that from the moves. So like this. Yeah, like that. Row column. I'm just basically making this row column, so we only do one calculation here. Let's see what, yeah, I want to do. I wanted to have a list of moves here, and I want to basically remove it as I take a move. So over here, yeah, okay, that's good. So we remove this move. But, I mean, basically we can also check, else print invalid moves. And then we just like exit. Yeah, so we could do that. Uh, Maybe we can just like even make a random move. So we can just like move equals to, we can then sample. We can make a move using the our moves here. Okay, and then after that, what we do? Okay, so that would be great. So actually, because we have this self dot moves thing here, we actually don't need to check this anymore. So basically, we can just do like, yeah. In fact, we don't even need this. We can just put it here. Yeah, because it's like quite easy to check this. And then we can return here. Okay, and return like that. Yeah. So we just basically after we open the mine, we just check whether or not we have won the game at the end. So define sample will basically be like return np.random.choice. In fact, we can even do this here. Self.sample. Okay, so that's good. Yeah, we can do it like that. Okay, so we can actually do our game loop now. While environment.done. Okay, this is called a random agent. Okay, it's a very typical example of an agent that you first create in order to test whether your code is working. So we do this while not environment.done. We step with the random move. Okay, and then we can maybe like render. Okay, and then at the end we just print environment.done. Okay, so there's something wrong. Like we are making random move too often, and display this. Okay, something is wrong with the environment.sample method. Like over here, they put invalid move, which is weird. Which is weird. If row times self dot wave plus column in self dot mines. No, it's here. Okay, let's remove this line here. I'm not too sure um, why there's this issue, but let's just check. if we do this, okay, there's something wrong with the move method. Actually, what we can do over here is that we now mine is 0. We can also do like if self dot moves. Row times row. Or because I actually uh, kind of accept the 0 0 case. That's why if row times row offset times self, I know why already. Times self dot width. Okay, I need to do something here. If row times row offset, okay. Actually, I think the original code might be neater. We can just use the. I think it's fine. Yeah. Row times row offset from self dot width plus column offset. If this is equals to if this is self dot moves, then we basically if this is a valid move, we can then step through. Okay, let's see whether it works. X not in list. Okay. Why is it printing out 45 and 65 though? That is so weird. Yeah. When I do my environment dot step, it's printing out some numbers which I did not program in, I believe. So I only did this. So now only when it's in the a list of valid moves, then it will step through one time and then basically open another cell. So let's see that. Okay, so now there's more. Okay, now there's still invalid move, which is weird. Okay, because we're not supposed to get that. Okay, we are just doing environment.sample actually, which means that we can actually sample the list of moves here, right? Oh, it's because of this one. I think this is so many invalid moves. Okay, so we get like 61 environment.step. Okay, let's try it. Okay, you see it's printing out a 55. Let's see. Where did this 55 get printed out from? Is it in this? I think it's because I did not return anything. Yeah, it's very weird that I'm printing out something. Oh, I know why. I forgot to put I forgot to put back the column plus column offset and row plus row offset here. No wonder it did not work. Okay, so now it should work. It's still printing out stuff though. I'm not too sure why. At least now there's no like invalid moves. Okay, let's just try again. Over here is printing out some stuff which I don't quite understand where it's coming from. Oh, I printed it here. Legacy code. Okay, now it works. So you can see like over here, we can actually print out the action and the okay, we can like print move. Yeah, so you can do this like 1 0, which is here, 3 0, which is here, and so on. The random agent hits the mines. Sometimes you see over here, hit a mine. I wonder if it's able to just like randomly solve it. So okay, so actually there's one thing here is that when we make our first move, we shouldn't be hitting a mine for the first move. So we need to adjust our mines accordingly. Okay, so basically, if yeah, we can do it, the self dot mines we can do it like here in the step. Okay, if the length of the self dot moves is the same as means is the first move. then just make random mine positions. Okay, let's just see where it leads us. So it takes in this move. So maybe I'll just print out like move. So it just takes random moves until it hits a mine. And see that this is about a 9 by 9 board with 9 mines. That's about 10% chance. Yeah. So most people should be able to solve it. But you see over here, it made obvious errors. Like it's not supposed to go here. Like once you see like two, you know that this two is definitely mines and these are safe. So there's some moves that can be done here that will lead to a win. Okay, so the random agent is not able to do that because it's doing it randomly. So it's to be expected of it. So we can actually see this is like one episode of a game. Okay, and now what we want to do is we are interested to create a neural network. Okay, that can take in this bot state. Okay, the bot state would probably be just like all the zeros and ones. Okay, and maybe another grid to say like what has not been opened. So it'll be like zero ones and okay, all these blanks here. I will need to think of a way to represent it in the maybe all these unopened squares can be given as minus one, zero, one, two. Yeah, we should probably give it a different class. Maybe we call it minus one, and then we see whether or not the neural network can actually learn from this bot state. So that will be something interesting. Okay. Yeah. Let's try to code this out in the neural network format first. Okay, because the current network itself, I don't think it can learn because it's not in the right format for the neural net. So one way to do it is to do like sort of one hot encoding, so that we actually encode the different bot states, okay, inside the neural network itself. So maybe we can have it like somewhere here. Okay, like define get tensor states. So what we'll do is we'll have like just import TensorFlow here. Okay, so we want to do a tensor whereby let's do an MP array first, then we can convert to tensor later. So okay, so what we do is we can have okay, so we can have like my board is this. Okay, so first up we can append, okay, in our tensor state we can just check what is the board position. So over here, do one hot encoding for the various numbers. Okay, so what we can do is we can do like the self dot board. We can do again self dot board one minus one. So we can do like maybe we can just call it a mini board. This okay, so it references the board's position, and then we can basically within my board itself, okay, we can append like we can append like ints like that. So this will be like 0 or 1. Okay, in range 9. So from 0, 1, 2, 3, 4, 5, 8, 7, 8. Yeah, so this is basically what has not been opened, then this is basically what has been opened. So maybe you can return mini bot, return my bot. So we can like get, we can start off with this to see what's, okay, it didn't work. Okay, try printing mini bot to see. Okay, mini bot is this. Okay, we can print mini bot equals to 1, equals to blank, and then we do like ints like that. So now we have true, false. We just want to convert this to, where was it? Here. Okay, looks like we can do it. We can do it like that. So we have this, and then we are like 0, 0, 0, 0, 0. Okay, which is weird. Okay, it should not be like that. So this should be actually broadcasted rather than, maybe use a mp.h stack in order to stack it up horizontally. Oh my, wow, what's happening here? Element wise, maybe it's a v stack instead of h stack. Okay, we can try the append method again. Okay, so we have numpy.array. We can have a shape here, I think. Yeah, maybe we just do a reshape here. That's weird. Why is this not able to be done? Everything here is zero, which is weird because like maybe I need to make my maybe I need to make my array with a string here for the moves. Yeah, like that. Okay, good. So if we put into a string, we'll see that everything is there. Yeah, so actually we don't really need to display the mines in this case because the mines itself don't really matter in this case. Yeah, the mines itself, basically the computer will know, okay, yes is good, no is bad. Yeah, the mines itself probably doesn't matter. So this one basically tells it what are the valid moves that needs to be done. These are the number of zeros. Zero moves, one mine moves, two mine moves, three, four, five, six, seven, eight. So we have defined our tensor state. Okay, so we can use a tf.tensor and wrap it around this. Yeah, we can do a tf.tensor around it. So yeah, let's do that. Oh no. Hey, my tensor is here. Okay, what am I missing? I'm missing value index and d type. D type is D type of element stored in this tensor, and value index is here, and index of operations endpoint that produces this tensor. Yeah, I think maybe we can just use convert to tensor. Converts. Okay, there we go. We have this either ones or zeros like that. So this signifies the board state. Okay, and then I think with that we can actually sort of like start to train our neural network in order to solve this game. So let's just do a quick check of our random agent. Okay, so looks like the game is more or less done. Okay, let's try creating an environment with like maybe only one mine. Oh, that was really unfortunate. There's only one mine and yet it still hit. Oh, hang on a minute. If there's zero mines, why are there still... Oh, okay, I know why. Because I did not do my mines generation correctly. So over here, we need a self.num mines. So if there's only one mine, okay, if there's only one mine over here, we need to adjust our end condition here as well. So so over here the length will be if the number of moves left equals to number of mines. So yeah, we have num mines like that. Self.num mines, we just checked here. And so we have a tensor state here that creates the board position that we want from the Minesweeper game, and then we just see what's the outcome. So here we won. So actually, what we can do is we can just do like that. Find play game. Okay, place the game and agent. Okay, so okay for game in range num games. Okay, we do an environment reset here. Okay, while not environment done, we do this. Okay, we don't need to print. Okay, just okay. So we can do like reward equals to 0, total reward equals to 0. Okay, so what we can do is the reward plus equals to environment.reward. Okay, and then at the end of it, we can just like print out number of wins in games will be total reward. Yeah, that's more or less it. Okay, so then we just need to define what's the environment and what's the agent. Okay, so over here will be, so the agent will take in the tensor state. Agent equals to what's this? Get tensor state. Okay, so we have an agent here, and then the agent takes in a tensor state. So first we need to define like stuff like random agent later that takes into account state of the game, and then basically we just need to output the moves. So actually, if the agent is smart enough, one of these cells will already tell you what are the moves left. But we can just give the moves to the agent as well. So then there's a return. Yeah. So this just returns a random action from the available list of moves. So of course we will create agents that will actually do better selection of moves, especially using deep learning. We will use the tensor representation that we come up with over here in order to do it. So but right now I'm just creating the game environment. So we have a play game function like that, with total reward like this. Okay, I don't print out at all. Maybe we can just put a verbose equals to false. Okay, if verbose we can print out. Yeah, we can print this out. Yeah. Okay, so this basically just keeps doing this for a number of games and then prints the total number of wins. Okay, and then yeah, I think more or less this is done. Random agent not defined. Okay, that's fair. Okay, let me just put this up here so that we run this first. Num games not defined. Okay, isn't it here? Num games. Because this is okay. So we have done this already. So we can actually call like maybe play game now. Play game with environment will be Minesweeper. How do I define Minesweeper? Minesweeper. Yeah. Minesweeper. A bot size of 9 with maybe 2 mines. Okay, agent equals to, so the environment will be like Minesweeper agent is the random agent. Okay, and the num games maybe we put as 10 or 100. Yeah. Okay, let's see. mp.random.sample moves. Okay, let's just print out the moves so that we can see what's wrong. Okay, so this is the moves, and then why can't we do a mp.random.sample? Oh, it's actually not sample, it's random.random.choice, because we are just choosing one of them from the moves from an array. Yeah, that's my bad. Okay, int64 object is not callable. Okay, let's just print out moves to just see. Okay, so if you want to do like this, mp.random.choice from a 1D array. So I guess this array is not a 1D array. Isn't it correct? mp.random.choice. I mean, that's what I did for my code earlier, right? I did this mp.random.choice self.moves and it worked. So like the self.moves will be like here, where you can actually have all the moves available. Okay, so that is something that we need to solve why this isn't working. So yeah, okay, why is this not working? Okay, why is this not working? Environment.moves should be a 1D array already, like that. And I just want to sample from that. So maybe let's see whether there's an issue with this. We can just do mp.random.choice and then we just do the array and see whether it works. Yeah, it works. So what's wrong here? Oh, silly me. I put agent equals to. So this should be move equals to. So okay, problem solved. It's just a wrong assignment. This should be move equals to this. And we do the step of this. So in a random agent with 2 mines, the number of wins in 100 games is like 1, which is uh, not very impressive lah. In to be honest, yeah. So let's try again. Okay, can have -1 reward. Okay, so this needs to be tweaked. Okay, so it's either 0 or 1. Okay, our reward doesn't need to be -1. Okay, let's try this again. Oh, no wonder it's like 1 because like they count losses. Oh, okay, let me just restart this whole thing again to just make sure that everything is working. Oh, with 2 mines, chance of winning is quite low. or random agent. I mean, which is to be expected. Minesweeper is a game of oh, did wrongly. It's a game of skill. So, I mean, mainly skill. But I think there's something wrong with this in the total reward here. So maybe it's because I only counted the last one. I It shouldn't be just one. It should be more than that. Like even with two mines. 48. Yeah, that's more or less it. If there's only one mine, the random agent should be able to solve it all the time because you open up everything already, right? Oh, only for the squares that is open up as yeah, because there are quite a few cases where you click and then you open up the whole board. Okay, but it doesn't solve fully. Okay, how about the 999 case? How well can a random agent fare? It didn't do very well. Okay, so I mean I could implement a rules based agent as I did yesterday. Okay, but that's not the point for the stream. Okay, what I want to do is I want to use this tensor here. Okay, and probably do some reinforcement learning method in order to optimize how to solve this. Okay, now I'll just be pausing the stream here, going for a short break. I'll continue shortly. And yep, see you all again later. Okay, bye.